Hello, my name is Jared Baldwin. I'm a senior computer engineering major, and today I will be giving you the background on Quicksort. Quicksort was developed by Tony Hoare in the early 1960s. Originally, he discovered this algorithm while studying machine language translation at Moscow State University. In addition, its simplicity allows it to be easily implemented. These attributes make it one of the fastest and simplest sorting algorithms. Like merge sort, it is a divide and conquer algorithm. Unlike merge sort, it can be implemented with arrays. It is also known as a partition exchange sort since it sorts an array by partitioning. On the downside, quicksort is not very robust, and as a result, errors in implementation may slip through, causing performance issues. Also, when partitions are unbalanced, it will run much slower.
Hello, my name is Tara Bazemore, junior computer engineering major, and today I'll be giving you the definition of a pivot. A pivot is an element that is used to separate a partition into two different sides. One that is less than the actual pivot and one that is greater than. Once you separate the elements into two different lists, then you do it again recursively. You then separate the side that is less than, also the statement that we did at the beginning. So you find a pivot, which is the middle element, or just a random element that is found in the list, and you separate it again into one that is less than and greater than. And you do that recursively until the side, or the less than side, is then separated into a sorted list. Then you come over to the greater than side, and you separate the list again into one that is less than and greater than. Again, with the pivot in the middle, which then gives you a sorted list. Once both sides are sorted, you can put the two together, and it gives you one big sorted list.
Hi, my name is Martin Blow. I'm a senior doubling in computer engineering and electrical engineering, and today I'll be going over the best case, average case, and worst case of quicksort. When evaluating quicksort, one of the main factors when determining runtime is whether the partitions are balanced or unbalanced. In worst case, one partition will have n-1 elements and one will have 0 elements. When solved, this leads to an arithmetic series which ends up equaling n squared, which is also the same as the worst case for insertion sort. The best case for quicksort occurs when each recursive partition is split in half so that no partition is of size greater than n over 2. In this scenario, the equation would be t of n is less than or equal to 2t n over 2 plus theta n. Master theorem case 2 tells us that if f of n is equal to theta n log base ba, then t of n is equal to n log base ba log of n. In this equation, a is equal to 2, b is equal to 2, and f of n is equal to n. So the equation would be f of n is equal to theta n log base 2 of 2 is equal to n. So we know from that t of n is equal to theta n log n. In the average case, each recursion of quicksort produces an even mix of balanced and unbalanced partitions. The cost of the unbalanced partitions can be absorbed and balanced by the balanced partition. So the overall runtime is still n log n, which is also the best case runtime for quicksort and also the best case for merge sort.
Hello, my name is Elena Anderson, a junior computer science major, and I'll be giving you the pseudocode for quicksort.
The first thing we do is start by creating a function called partition. Within this function, we're passing through the array and the size of the array. After you have created the function, we go on to make an if statement. If the size is less than 2, we return the array because it's already sorted. Next, we randomly generate a pivot. After generating the pivot, we set a lower and upper index to the least and greatest indices in the array, which you can see pictured as the two gray boxes. The major component of the pseudocode is the while loop, which runs until the upper and lower indexes are equal. It ultimately separates the array into the two partitions of being lower or greater than the pivot. As you can see on the while loop on the screen, the lower index skips over elements that are less than the pivot, and the upper index skips over elements that are greater than the pivot. Whenever the lower index reaches a value that is greater than the pivot, and the upper index reaches a value that is lower than the pivot, the two swap, which you can see in the swap function represented on the screen. When lower and upper equal, the array is partitioned. We then call partition on each of the new partitions recursively, which eventually sorts the whole array.
Hello everyone, I'm Trevon Bland, a computer science major. Today I will be showing you the visualization of quicksort. I'm going to teach you quicksort using numbers. First, we start off with finding our pivot. We can use any number as our pivot. We chose 3. We also set pointers on each end of the array. We have pointer A and pointer B. Pointer A is set at the left end at the number 6. Pointer B is set at the right end at the number 4. Next, we check each pointer to see which number is greater than or less than the pivot. So we start off on the right with pointer B. Number 4 is greater than the number 3. So we leave 4 in its place. We move B to the left 1 space. Next, we check pointer A. Pointer A is set at number 6. The number 6 is greater than the number 3. So we swap 6 with pointer B, which is number 2. Next, we move A to the position closest to it, to the right. Next, we check pointer B, which is set at the number 7. Number 7 is greater than our pivot, 3. So we keep 7 in its place and move the pointer B to the left 1 space. Next, we check pointer A, which is number 5. Then we also check pointer B because the number 8 and the number 5 both are greater than 3. So they stay in the same position. Then we move pointer B to the number 1 and keep A at number 5. So we check the number 1, and the number 1 is less than the number 3. So we swap number 1 and number 5. Now we are done with our pivot 3. So we move to the left side of 3. We have 2 numbers, and the pointers A and B are set at number 2 and the number 1. We made 1 our new pivot. We check 2. 2 is greater than 1, so we swap 1 and 2. Now we have 1, 2, 3. So this side is done. Next, we move to the right side. We find our new pivot, which is number 4. We set our new pointers, A and B, at each end. A is set at 5, and B is set at number 4, which is also our pivot. Next, we check the number 5 to see if it's greater than our pivot, number 4, which it is. So we switch the number 4 to number 5. Therefore, 4 is now a complete set of numbers. So we move down 1. Move to our next step. We find a new pivot. Number 7 is set as our new pivot. We set our pointer A at the number 8 and our pointer B at the number 5. We check the number 8 with the number 7. The number 8 is greater than our pivot, 7. So we switch 8 to number 5. And now we have 5 in our complete set of numbers. Next step, find a new pivot, which is the number 6. We set our pointers, A and our pointer B, at the number 7 and the number 8. So next, we check our pointer B, the number 6. 8 is greater than 6, so 8 stays in the same place. So we move our pointer B to the number 6, which is also our pivot. We check the number 7 with our pivot, which is 6. 7 is larger than 6. So we switch 6 and 7. And then we finally have our complete set of numbers.
This is a real-life example of what a quicksort would look like by organizing it by our name. I am pointer A.
I am pointer B.
And I am the pivot.
Pointer A is shorter than the pivot, so I will stay where I am.
Pointer B is taller than pivot, so I will stay where I am.
I am now the new pointer A, and I am shorter than the pivot, therefore I stay here.
I am the new pointer B, and since I am taller than the pivot, I will remain in the same position.
Now that I am completely sorted, each side will turn into the partitions.
I'm pointer A and also the pivot.
I'm pointer B.
Since I'm taller than pointer B, we switch.
I am pointer A and also the pivot.
I am pointer B.
Since I am shorter than pointer B, we will switch spots.
So, we are all
Sorted! Quicksort is a great general purpose algorithm that integrates simplicity and speed. When partitions are balanced, it provides optimum performance. Unbalanced partitions cause it to run significantly slower. All in all, Quicksort remains a popular algorithm due to its advantages and its ability to compute efficiently on average. Thank you.
Hello, I'm Jerome. What's my name? Hold on.
Hi, my name is Tara Bazemore. I'm a computer junior major, and today I'll be giving you the definition of pivot.
We check number 4. And 4 is less than 3. 4 is greater than 3, not less than 3. Hold on, man.
I am now the new pointer A, and I'm smaller than the pivot. Therefore, I stay here.
I am a now new pointer B, so now I stay in the same position since I'm taller than the pivot.
Y'all can walk with me then, like y'all stand right here, like I'm shorter than the pivot, and then you move back.
Let's do it a lot.
I am the new pointer A, and I'm smaller than the pivot. Therefore, I stay here.
I am the new pointer B, and I'm taller than the new pivot, so me and him have to switch positions.
Since I'm taller than pointer B, we switch.
I am pointer A and also the pivot.
I am the new pointer B.
Since I am shorter than pointer B, we will switch spots.
Alright.
Since I am shorter than pointer B, we will switch spots.
And we are now sorted.
Let's turn sideways.